the other day I had just started to introduce the Giddings-Davis statistical overlap theory, which is a big advance on the concept of peak capacity. At least that's one way you can look at it. The peak capacity is the maximum possible number of peaks that you can fit in your separation window, separation time or separation volume, or whatever units you want to use. But it essentially requires that all the peaks come out in a sequence, in a regular way, a non-random fashion, a fixed fashion as they come out of the column. The statistical overlap theory, on the other hand, says that the peak positions in time or volume realistically are not uniform, but rather they're random, that they constitute a random distribution. And the space between two peaks can be tiny, they can be totally overlapped, or the space between two adjacent peaks can be quite large. And this has a huge effect on the number of peaks that you can actually observe, and an even bigger effect on the number of peaks that will appear as a pure component. In fact, the majority of the peaks, once you have a significantly large number of peaks, come out not as single pure components, but as highly overlapped peaks. And the question is, how bad is it? And statistical overlap theory addresses that question of how many peaks will you actually observe? So this approach, I gave you the reference the other day. We started in a 1985 paper by Cal Giddings and Joe Davis. There must be at least 50 papers that follow on from there, elaborating the ideas in greater and greater detail, in going from simple one-dimensional separations, which is what we're talking about now, into multi-dimensional separations. It includes using different kinds of detectors and just lots and lots of detail, but the basic paper really has the essence of what I think most people need to know about. So we'll talk about some of their results. And then we'll move into this gigantic issue, hugely important issue, of the extra column contributions to the apparent width of a peak. And we'll talk about the effect of the extra column factors on the width of the peak, the height of the peak, or the area of the peak, and perhaps most importantly, we'll talk about the effect of extra column broadening on your resolution. If you don't set your equipment up the right way so that you minimize the effect of extra column broadening, your resolution can be very seriously degraded. It's going to be much worse than what it ought to be. And in particular, we're going to talk about two problems today. We're going to talk about the problem of what happens if you inject an excessive volume of sample, and what happens if your detector time constant or the size of the detector is too large. There's a very important additional effect, and that is what happens, how much broadening happens in the connecting tubing between the injector and the column, and between the column and the detector. But we don't have the background yet to understand the details of that. We'll get into that probably in about a week and a half or 2 weeks from now. So what statistical overlap theory is all about is when the retention times are not regular, but are random with respect to one another. And in fact, Davis Giddings believed that the correct kind of random distribution is what we call a Poisson type distribution. And that's a distribution that looks something like that. It's not Gaussian, it's not symmetrical, it's not flat. It goes up relatively rapidly and then it comes down slowly. So it's a fairly peaked distribution. But it's the kind of distribution that you get when you do counting statistics. So, just to start on the simple case, here's what a set of 20 peaks would look like if they were absolutely regular, if there was no randomness to their positions at all, that they're all equally resolved, and that all of the peaks have exactly the same height. And we can get 20 peaks of this width in this amount of room. Now, what happens is if I keep the widths of the peak constant and I keep the spacing the same, but simply allow the peaks to have different heights. Well, if you do that, then of course the peaks that you plot are going to have different heights, but they're also going to overlap to such an extent that you might not even be able to count a peak. But in this case, there is something like 19 peaks which can be resolved. And each of these vertical lines corresponds to the position of a peak maximum, and so on. But you can see here, we don't even really form a peak. And this is just barely a peak. And this shoulder is just barely a peak. You would say there's a peak there, but if the ratio of heights was a little bit worse, you wouldn't even see those peaks. So the relative heights of the peak can have an impact on whether or not you see a peak, because the resolution may not be good enough to see a minimum between the two maxima. This is what happens, it's an example rather of what happens if you allow the peaks to have all the same width and all the same height. Because of the overlaps between them, because they come out at random times with respect to one another, there's a whole bunch of them right here that come out so close together that you really only see one maximum. And this is the situation addressed by SOT theory. If we allow both the heights and the retention times to vary randomly, then this is an example of a distribution that you get in that situation. This is a little bit more difficult to treat, but SOT theory the detailed theory does allow you to treat cases where the height and the positions vary randomly. But we're just going to consider the situation where the positions vary randomly. Okay, so the question is, how many peaks will you see? Now, because the positions are random, you can only talk about the number of peaks that you will see on average. So we're talking about the average of an ensemble of a large number of these types of statistical calculations. But the math can be worked out, and it turns out that the answer for the average number of peaks that you'll see, little p is the number of peaks, m is the number of real chemicals, real components present in the sample. So the average number of peaks that you will see is equal to m times the exponential of minus m, the number of components, divided by the peak capacity of the column. This is the peak capacity for a uniform distribution of peaks. So it's a negative exponential. So if it happens that a peak is pure, you count it once. If a peak has two components but there's only one peak, count it once. If a peak has 10 components in it but there's only one peak, you count it once. It's the total number of actual maxima that you will observe on average. Now, what we're really interested in, this ratio of m to the peak capacity occurs over and over and over and over again in statistical overlap theory. And so it's given a name, and it's called the saturation factor. Now, S is the number of singlet peaks, that is the number of pure component peaks. These peaks then are analytically useful because they're pure components. And the only difference between the equation for P and the equation for singlets is a factor of 2 in front of the saturation factor. Because of that 2, the number of singlets decreases much more rapidly than do the number of total number of peaks that you see. Now, given that this m over nc is in the exponent and it's a negative exponent, the lower your saturation factor is, the easier the separation will be. Now, if you had a peak capacity of, let's say, 10, and you have a two-component mixture, that's a fairly easy separation. The saturation factor would be 2 over 10, 0.2. If you had 4 peaks, that's a tougher separation. And the exponent of this equation is going to be minus 0.4 if you have 10 units of peak capacity. So the larger the number of peak capacity units you have, the more likely it is that you will isolate peaks that are pure single components. So in general, you want the number of units of peak capacity to be a lot bigger than the number of components in the mixture. Or to put it another way, the more complicated the mixture is, the harder it is to do the separation with a system with a given peak capacity. Here's a particular example. We're going to assume that there are 20 real components, so m is equal to the number of real components. And I'm going to plot the average number of singlets versus the peak capacity. Even if we go all the way out here to a peak capacity of 200, 10 times the number of components. We're still going to see considerably fewer than 20 peaks. I'm sorry, 20 pure peaks. It's on the order of 16 pure peaks when your peak capacity is 10 times higher than the number of components. That this is not a favorable situation. Now, what it says in the long run to us is it's very, very unlikely that you will ever get a separation to work if you don't deliberately adjust the conditions to improve the band spacing to make it non-random. Mother Nature throws a random mixture at you. It's your job to arrange those peaks by changing the column type, by changing the mobile phase composition, by changing the temperature, by doing the right temperature program, by doing the right gradient dilution program. That's where the work is. This is a related plot. Instead of plotting now versus the peak capacity, we're plotting versus the number of components. And so this is the average number of maxima. This is the peak number, P, versus the number of components. And here we're going to assume that we have a peak capacity of 100. The maximum number of peaks that you're going to see here, on average, is going to work out to be about 37% of your peak capacity. This is the best you can do. Think about it this way. Suppose you have 100 units of peak capacity and you inject a single component mixture. There's only one substance. You're bound to get a pure peak. If you inject two compounds, you have 100 units of peak capacity, you have a pretty good chance of getting two pure peaks. But the more components you put in there, you're going to see more peaks until you have so many components that the chromatogram becomes so overcrowded that you start to decrease the number of peaks. So there's a trade-off. So there'll be a maximum in the plot. We can do the same calculation for the number of singlets, i.e. pure peaks. It turns out that the maximum number of singlets that you can see is 18% of your peak capacity. And the singlets are the peaks that you can analyze for. The peaks which are vastly overlapped, you really can't analyze for those compounds. You've got to split the peak. You've got to resolve those mixtures better. Okay, so those are the basic ideas behind the statistical overlap theory. This is the essence of it. As I said, the literature is loaded with papers on this subject. It has become a very important topic, especially when we're dealing with really complicated mixtures. Okay, so we're going to move on now to extra column broadening. Here's my attempt at the simplest possible block diagram of any chromatograph. If you can make a chromatograph work with fewer components than this, let me know. Every single part of the instrument can degrade the separation that you get in the column. I mean, this is where the separation takes place. If over here in the detector you inject too large of a volume, that can screw up your separation. If your detector has a time constant that's too long, or if the volume of the detector is too big, that can screw up your resolution. If you set you can take the data system takes data at a certain rate, so many data points per second. If you set the number of data points that the data system takes at too few points per second, that can screw up the separation. If the volume of your transfer tubing, either between the injector and the column or between the detector and the column, is too big, that can screw up your separation. There's more chances to lose here than there are to win. You have to understand the interactions between the injector, the column, and the detector and the column, and the transfer tubing and the column. And we're going to talk today about the injector and the detector. The only place in this diagram where you can't go wrong is the line connecting the detector to waste. You've already acquired the signal. You can do anything you want there. Don't worry about it too much. Just don't get a leak. Okay, so this says again what I just said. Every single part of the system can, in principle, cause any parts of the system. Here's another way to say it, but a bit more arithmetically. What you observe at your detector, what gets plotted out by your data system, the width of your peak that is printed out by your data system, the number of units of plate the plate count that's printed out by your data system, all of those are influenced by all of the components of the system. So this is really what we observe. Sigma squared total is the total variance that's plotted out by your data system. That is equal to the sum of the square of the contribution of the injector to the variance. The column, the tubings, the detector, volume, the detector time constant, the data system time constant, I'll lump in with the detector time constant, and I'll just call it time constant. Now there's two important things here. Number one, it's additive. Number two, these are squares. Squares of any kind of number is a positive number. There's no cancellation of errors here. And keep in mind that it's the square. It's not sigma total equals sigma inject plus sigma column plus sigma plus sigma. That is wrong. You have to add the square. Now, imagine that one of these quantities was, one of these sigmas is 10 times bigger than any other sigma. Well, the 10 gets squared. So even though you have 4 or 5 other sigmas and they're all 10 times smaller, their square amounts to about 100 times smaller. And so they become negligible. So the square is actually helpful because it says more often than not there's one dominant term. And guess which one we want to be dominant? We want the column to be the major contributor to the peak width. Now, you don't want to deliberately make the column big because that means then that your plate count is going to be reduced because the plate count is your retention volume squared divided by the square of the total, the variance, the standard deviation squared. So if you made this deliberately big by making this big deliberately, this is going to be too small. But at least, because you're adding the squares, you don't have to be completely and totally paranoid and make all of these other things minuscule. They simply have to be small compared to what the column contributes. That's the big picture. Now we got to get into the microscopics of it and see how these things relate to the physical parameters of the injector and the detector today. So the first issue we're going to take up is that of excess sample volume. And what we're going to do is assume that the sample gets loaded onto the column as the simplest possible shape. And that's a pulse. We're not going to get fancy about the peak shape. We're going to say that the sample comes on and it gets loaded, and so it goes from 0 to 1 and back to 0 again. Now, I have never seen an injector ever behave this way. They behave like that, or they behave like that, or they behave like that. But the rectangular pulse is the simplest possible model. So that's what we're going to use. Now, what happens then is that this input is loaded into a column, and the column operates on that pulse. And if you want to think of it in the following way, it's a good idea to do it. Think of the column operating on a series of much narrower pulses, and the resultant is the sum of the response of the system to all of these individual narrower pulses. So I'm now showing you the result of an exact calculation. I'll show you the equations for this later. I don't want to show you the equations right now. So, in peak 1, which looks really Gaussian, what I'm doing is I'm injecting 1 unit of sample volume. The units of sample volume are in milliliters. And my Gaussian peak has a retention volume of 100 mLs, and the sigma of the column is 1 ml. So what I'm saying is, if you inject 1 ml into this column, you're going to get a peak that looks very Gaussian. You're going to get this peak. If you inject twice as much, what you're going to see is the area under that peak is going to exactly double. Why has it doubled? Because you've injected twice as many moles or twice as many grams of sample. The injection volume went from 1 ml to 2 mLs. If you look at these two peaks carefully, there's the maximum and there's the maximum. This second maximum is actually shifted out a little tiny bit. And if you were to put a ruler on this, you would see that the second peak, the half width of it, is a little wider than the half width of the 1 ml peak. Now, if I inject more, and I go up to this situation where I've injected 5 mLs, this peak maximum is out further, the width is increased more. But notice, this peak is not twice as big as this peak. It's somewhat less than twice as much. If I inject 7 mLs, that's this peak here. And now when I inject 10 mLs, I have a much taller peak than I started with. My peak area is 10 times as big as the one I started with. The peak width is a lot wider than what I started with. And the top of the peak is now flat. There's a plateau. And if I inject a larger volume yet, say I inject 20 milliliters, the height of the peak is not going to get any bigger. The reason is you've totally flooded the column. What's coming out of the column is the same concentration as what's going into the column. And it can't possibly exceed that. That would require you to make mass inside the column. It would be the opposite of destroying mass. This peak and this peak and this peak are obviously not Gaussian peaks. Now you know why I didn't want to show you the equation. Because our doesn't matter what function this is, what matters is that the concentration here is a function of V star, where V star is the volume of the rectangular pulse. The bigger the volume of the rectangular pulse, the peak maximum goes up and up and up and up and up until it reaches a limit, until the peak maximum concentration becomes equal to the concentration that you're injecting. And at some point, the peak width essentially becomes independent of the sigma of the column and is totally dominated by the width of your injection pulse. Now, the only way you can make sense out of this particular function is to plot it like that, and it produced those curves. But there is a way of looking at these peak function equations that generally produces a much simpler and easier to understand answer. And that's in terms of what we call the peak moments, M-O-M-E-N-T-S, moments. This V bar is the average peak volume. If I take the equation for a Gaussian peak and put it in here for this concentration as a function of time, and in the denominator for the concentration as a function of time, and in the numerator I multiply it by the volume to the first power, and then integrate with respect to dV over all volume, that gives me the position of the center of the peak. It's the average. It's also called the center of gravity, the center of mass, and mathematically and statistically it's called the first moment. If I put in the equation of a Gaussian peak, this V bar is equal to VR, the retention volume of the Gaussian peak. If I looked at this as a function of time, and I put in the Gaussian as a function of time, and did the integration as a function of time, this would be the retention time of the peak. If instead of computing, I call this the first moment, that's the first moment, you can generalize this operation, this integration, and instead of multiplying by v to the 1 power, multiply by v to the n power, and that gives you the nth moment of the peak. By the way, the denominator, we're not multiplying the concentration by any volume to anything, we're multiplying it by 1. V to the 0 is 1. So that's the 0th moment of the peak, but it's simply the area. The area under the peak. And for all of the higher moments, the denominator here is always m naught, the 0th moment, the area under the peak. Now, by the way, let me do a little sketch here. So here's volume. And there's my peak. When I compute a moment this way, multiplying by v to the n, I'm really computing the moments of the peak about the 0 point of the horizontal axis, whether it's volume or time, doesn't matter. I'm computing the moment of this about that. If this seems unfamiliar to you, I tell you to go back and look at your physics courses, in your beginning physics, and you calculate things like moments of inertia, and you'll see the same darn equations. They turn out to be identical concepts. And this would be, if I calculated this number here is the center of gravity about 0. But you can calculate a moment about anything you want. And it's frequently the case that for the higher moments, like the second moment, we compute the center of gravity, we compute the moment about the center of gravity. So we're actually going to compute the moment. I just really did a bad job of getting that through the center of gravity. There's the center of gravity. This, remind me to fix that. That equation is wrong. It's v minus v bar, the whole quantity squared. This is the moment about the center of gravity. And this quantity, m2 prime, is really related to the variance of the peak. If we put in the equation of a Gaussian, the second moment about the center of gravity is simply the sigma squared of the Gaussian peak. The take-home messages here are the following. The first moment of a Gaussian peak is identical to its retention volume, Vr. The center of gravity and the position of the peak maximum exactly coincide. Not approximately. They are bang on. The second central moment about the center of gravity is the sigma squared of the Gaussian peak. Now, what we're going to do is the same exact mathematics to this mess. But I'm not going to turn the algebraic crank for you. I'm just going to give you the answer. So we're going to determine the first moment of this peak. Oh, sorry. We're going to start with the 0th moment, which is the area. And the area, it's a rectangular pulse input. The height of the pulse is C0. The width of the pulse is V star. The area, obviously, is C0 times V star. The first moment works out to be the retention volume of the Gaussian part of the system, the column, plus 1/2 of the volume, the rectangular pulse width divided by 2. In fact, this is the first moment of the pulse, which makes sense. If you have a rectangular pulse, the center of gravity is half its width. The second central moment is the sigma squared of the Gaussian, that is the sigma squared of the column, plus V star squared divided by 12. And that's not an approximation. It's exactly 12.0000. This turns out to be the second central moment of just a pulse. What this is saying is that the moments are additive characteristics of the underlying distribution. So, what have we learned? If I increase this, my area gets bigger. You saw that when I drew all the curves. If you increase the injection volume, the peak V star, the peaks get wider. If you make sigma squared negligible compared to V star, then the width is totally dominated by the width that you inject. And you don't have to mess around, I'm sorry, I have it written up there. You don't have to worry about that ugly mess. The moments are much easier to deal with than is the actual mathematical solution of the problem. Now, if you had an input which was non-pulse, for instance, if you had if your input looked like that, I guarantee you that this would be the area under that. This would be replaced with the center of gravity under this, and if it's a symmetric triangle, then it would be replaced by that distance there. And the second central moment would be sigma squared plus the second central moment of that distribution. If you had some real wacko function, all you got to do is determine its area, determine its center of gravity, and determine its second central moment, and you add them to the values for the Gaussian part of the column, and you have the answer. And you don't have to deal with anything like that. Okay, forget about it. Now let's see where this gets us. This is what the concentration at the exit of your column is going to look like as you increase your sample volume. If you inject no volume at all, you get no signal. Nothing can come out. Put nothing in. Inject a little bit, you get a linear response. You double the volume injected, the area doubles, the concentration at the peak maximum doubles. The peak gets a little bit, tiny little bit wider. Once you're into about 2 times sample volume equal to twice your sigma V of the column, you start to see some curvature here. And so if you inject more, you don't get a proportional increase in the peak height, but you do get a proportional increase in your peak area. When you're injecting about 5 times as much volume as the sigma V of the peak, this curve is essentially flat. You get no further increase in the concentration at the peak maximum. The peak simply gets wider and wider and wider as you inject a bigger and bigger and bigger volume. The plateau gets longer, if you will. This has an awful lot to do with your analytical sensitivity. If you inject a microliter versus a tenth of a microliter, you're going to see a peak which is a lot bigger in area and a lot bigger in height. If you inject a 10 microliter sample, you're not going to see a signal which is 10 times bigger than a 1 microliter sample in height, but it will be 10 times bigger in area. To get a lot of signal, you're always pushing to inject as much as you possibly can. But obviously you can inject too much. Okay, that pretty much says what we need to say about the injector end of the system. There's a lot of different ways we can talk about or treat the detector time constant broadening, but I'm going to assume that what we have, that the detector behaves as a very, very simple electronic filter. And the simplest filter I know of is the capacitor resistive filter, frequently called just an RC filter. Here's my input. The input is measured with respect to ground, and here's my output. Now we're not dealing with chemicals now, we're dealing with electrons that are coming out of the detector into the data system. And I'm saying this is a model of the speed of response of the detector. And this has a time constant T equal to R times C, and the units of this are, of course, seconds. I'll call that time constant tau. Now, electronically speaking, if you go into an input of an RC filter with an impulse that is a very, very, very narrow pulse, pulse goes up, goes flat, comes down. An impulse is a pulse function which has essentially zero width. So the signal going into this is going to look like that. What will come out of this is a signal that looks like that, and we can describe that signal as exponential t divided by minus exponential t over tau. This is the simplest possible low-pass filter. If you had electronics and physics, you probably beat this to death in your physics lab. In instrumental analysis, we talk about this sort of thing at some length. So what I'm going to do now is the signal that comes from my chromatographic signal isn't that. My chromatographic signal is a nice Gaussian signal. I'm going to take a Gaussian signal and put it into this low-pass filter. So there's my low-pass filter response. I'm going to put a Gaussian into it now. And this is what I'm going to see. This is with a time constant of 0, and this is with a time constant of 1/2 of a second. The sigma of the underlying Gaussian is 1 second. So even if the time constant of the detector is a smaller number of units of time than the width of the peak in sigma units in time, there is some influence, and this peak maximum is diminished. It's less than that. And this peak is shifted. It's at a slightly longer time than the underlying Gaussian. And in fact, it's a little tiny bit asymmetric. What's not obvious is that the area under this signal is identical to the area under the parent Gaussian. I absolutely guarantee that. A filter does not destroy signal. It must come out. What goes in comes out. If I make this time constant longer, that means I make the device slower, and I kick it up to 1 second, the maximum is now lower again, the peak is wider, and it comes out later. And if I make it longer again, you're really doing a lot of damage to your signal at this point, a lot of damage. Now, the question naturally arises is why, if I know that this is going to happen, why not make the time constant 0? And the answer to that question is that all real signals have noise. And all real signals require filtering them to reduce that noise, filtering them to a certain extent. But if you over-filter, you do more harm than good. So I've plotted my Gaussian, which is the blue, is the input with noise on it. And the output is pink, and that's the output with 1/2 a second time constant. If I increase the time constant, a price of having more distortion of my signal. And if let's suppose I have two peaks that are close together. You can see that this valley here is deeper than that valley there. So if you have peaks that are close together, not only are you making the peaks wider, but you're destroying part of your resolution. And that's another big problem. So you have to set the time constant to be just enough to reduce the noise, but not too much so that you screw up the resolution of any pairs of peaks that are really close together. The same sort of thing would happen with using injector volume. If you had two peaks that were close together and you inject too much volume, you can diminish the resolution, the valley, between the two peaks that are separated. You want to increase the volume to get more signal, but you increase it too far and you screw up the resolution. This is just a fundamental fact of life. Whatever you do to get more signal has an influence on your resolving power. So you want to set it at some optimum level. There is no number, no one number that sets the optimum level. It all depends upon the sigma of the peak. Okay, sorry, wanted to get to here. We got there a little late.